All right, we're going to pick up in section 10.4 where we left off, which was with example number 3. If you'll recall, in this section we're talking about polar coordinates. And just as a reminder, polar coordinates measure the location in our xy plane by using a distance away from 0 and an angle measure that's away from the positive x-axis. And the distance from 0 moves right as the positive direction. If we were moving left, the distance would actually be r, that is, would actually be negative. And so when we do this, we have multiple representations for every single point in the xy ordered plane, right? All that works the same. And then we have these equations down here in the bottom right-hand corner that talk about how to change into and out of rectangular form. That's the one we're familiar with. And polar form, that's our new form. Okay, and so we had done a couple of examples where we changed points, and we're going to do one more. Right? We stopped with 2. Yeah, okay. So we're going to actually go the other direction on number 3. So our example, we're going to find 2 sets of polar representations of the given rectangular point. And the rectangular point that we're going to start with is the ordered pair 3, 4. So we can do this from a graphical perspective. That's part of what we can do. We can also do this from the equations perspective. So let me just talk about it from a graphical perspective so that you have some sort of sense of what that looks like. And then we'll use the equations to actually find the coordinate values. So if I have a xy axis, my point is supposed to be 3 and then 4. And I'm right up here in space. And you can imagine that down here, this is my 4. And over here, right, from the distance over here, this is 3. So I should be able to find the distance back to the origin using what? Yeah, the Pythagorean Theorem. And in fact, that's exactly what the one of the equations are that we're going to be using. The equation that was given to us was that x squared plus y squared equals r squared. So we're going to start there, whether you think about it from a graphical perspective or a formulaic perspective, to find r. So our x is 3, so this is 3 squared plus y is 4, so it's 4 squared. And what is 3 squared plus 4 squared? Yeah, it's 25. So my r value is what? Yeah, it's either positive or negative 5. Now, you might say, well, but we're talking about distance, shouldn't it just be positive 5? So it could be, but remember, we're trying to find multiple representations, right? 2 representations specifically for this anyway. So one of them we could go with 5, and the other one we could go with negative 5. That's one way we could do it. Certainly not the only way, but it would be an option. So I could take a look at those values for r. I also need a value for theta. So we have a second formula that we can use, either from the perspective of the triangle, which is where the formula comes from, or just by looking and thinking about formulas themselves. So the tangent of theta is supposed to be y over x, so y is 4 and x is 3. And how can we find what the theta value is? Because this is not a nice, like, unit circle kind of value. So what do we do to find theta when we don't have that unit circle perspective? Yeah. We do inverse trig function. So this one's inverse tangent of 4/3. So in your calculator, you'll need your calculator to find that inverse tangent of 4/3. And we'll use 2 decimals. If your book or WebAssign or something asks you to do something different, just follow their lead. So for what we're going to do on the board, we're going to do 2 decimals. This is approximately 0.93. Now, if you think about our unit circle kind of perspective of our coordinate plane, this is the measure 0, this is the measure pi halves. Pi is about 3.14, right? So pi halves would be about 1.57. So the 0.93 makes sense, right? It's between 0 and pi halves. So one of our ordered pairs that we can find is very nicely 5 and 0.93. Now, we're supposed to find two of these. So one additional option is that we could just add 2 pi to this, right? And I would spin around again, and I'd find another one. And I could spin around again, and I could find infinitely many points that would have this coordinate value. So if I add 2 pi to this, for example, I could get the ordered pair 5 and then 7.21. That's fine. So that can be your go-to. Or you could take a look at thinking about it from that -5 perspective. And then there's a couple options. So from the -5 perspective, it would actually mean that you went to the left 5. So let me go this direction. So imagine I went over here to the left. You could go all the way around, go clockwise or counterclockwise, depending, and you'll get 2 different answers, right? So if I go this way, what would I do to find that angle measure? Yeah, we'd add pi to it. So we would have the 0.93 plus pi instead of plus 2 pi, and I'd have 4.07. So that would be an option. I could go the other direction, true. I could go backwards, if you will, and go clockwise. So if I went this direction, how would I figure out what that angle measure should be? Might be worth noting they'd be negative, right? Because I'm going clockwise instead of counterclockwise. So it would be negative, but how could I find out what it's supposed to be? What is it if I go all the way like that? That's pi, correct? And I know part of the value to get there, this piece right here, is 0.93. So could I find out the missing piece? I should be able to, right? This missing piece right here should be pi minus 0.93, and then it'll be negative. Or, more accurately, we actually could take the 0.93 minus pi, and that would give me the value with its correct sign. So it'd be negative 2.21. So I don't bring this up to try to confuse you, I promise, but just to see that there's just lots of options that you could use, and they're all equally correct. There's not a one right answer kind of thing. It wanted us to give 2 answers, so these 2 are probably the first most natural choices of ways to do them, but they're certainly not the only ways to do them. Okay, any questions on that? Okay, we're going to look at some interesting graphs today because polar graphs are far more interesting than the things that we have been working with in rectangular systems before now. So let's take a look at, you're going to need your graphing utility, so your calculator. So it says to use a graphing utility to graph the polar equation as we're doing that, we're going to have to do the next part by default anyway. We're going to have to find an interval that works. So find an interval over which the graph, and then this is the part that is not sort of a by default, but over which the graph is traced exactly or only once. So we're working with a lot of trig in this, right? I mean, that's kind of the benefit of working with polar coordinates is that I have the ability to use a lot of my trig functions. And the thing is that when I'm using my trig functions and I've got theta that's going on like in this problem, right, it's going to keep going round and round and round. Whatever the object is, if I let my theta go on indefinitely, the graph never stops. It keeps tracing itself over and over and over again. So our goal is to try to find some sort of a window where it stops tracing itself over again. I want it to only trace itself one time, okay? So go ahead, and I don't remember if we've done it in class. Have we put things in polar coordinates yet? We know we did parametric. Hit mode. And if you've still got it in parametric form, it says function, it says func, par, pol. Okay, so FUNC, that's what we're normally in, have been up until now. Parametric's what we started with a couple of the class periods ago. Polar's where we are today. So change it to the POL. And once you do, hit Y equals, and what do you notice? They're R's, right? All right, so we're going to put in this equation that it gives us. So 2 minus 2 cosine of theta. Now, it seems reasonable because my angle theta is just theta, right? It doesn't, the angle measure is not like 5 theta or something like that. It's just theta. It seems reasonable that our angle measure would just go from 0 to 2 pi, doesn't it? Right? I mean, that should encompass all the values. Once we get to 2 pi, it should start repeating itself. So it's a reasonable assumption, and so we're going to start with that assumption. So if you hit window, you'll see you've got a theta min, theta max. So start with 0 and go ahead and go out to 2 pi. In terms of the graph, these are not big values, right? I've got 2 minus 2 cosine theta. Those values themselves, if I didn't have the 2's, I would be trapped between -1 and +1 on my x's and my y's. So I'm not affecting the values that much in terms of the x and the y's. So maybe like a -5 to 5 or -7 to 7 or something like that would probably be sufficient. So I think I've got mine set, as -5 to 5. And I want you to graph it, but while you hit graph, what I want you to do is I want you to watch when it stops, when the graph itself stops, and when the little cursor thing in the top right-hand corner that tells you that it's working stops. They should stop at the same time if we've chosen a correct interval for theta. So it's kind of like scrolling up here in the corner, and you've got the graph going, and they stop at the same time. So we do have a good theta value for this. So the theta itself is going between 0 and 2 pi. Now, just for fun, what I want you to see is what happens if you've chosen a value that doesn't work. Obviously, if the value is short, like you only went to pi, you're just not going to see the whole picture, okay? But what I want you to see is what happens if you've chosen something too big. So hit window, and instead of going to 2 pi, for the moment, just make it 3 pi or 4 pi, okay? Something bigger than 2 pi. And again, hit graph, but as you hit the graph button, I want you to watch how the scrolling happens while the graph happens. So the graph will look like it stops graphing, but the scrolling up in the top right-hand corner continues to go. That's how you know that it's too big, right? It's tracing over itself a second time. Okay, so you can change it back if you'd like to be to 2 pi. I don't know that we need it again, but we're going to sketch our graph on the paper. So it is a sketch. We're trying to be, reasonably accurate, but it looks like, kind of looks like a Roma tomato. Do you guys know what a Roma tomato is? It's the little like oblong-y tomatoes. Yeah, that's really what it looks like. It looks kind of like this. It's not a great graph, but something. The screen looks like it's a little bit more elongated on my screen, but that's because you've got that rectangular versus square window. If you wanted to square up the window, you could tell it to do window, I think it's zoom. Zoom 5 is zoom square, and it would give you more of a square picture, and you'd see that it looks a little bit more like Bob the Tomato, right, from VeggieTales. So it looks something like this. It doesn't quite, in fact, I think my graph's not great, but I think my graph looks like it's not hitting the 0, but I think it does. So let me just double check on that. I'm going to zoom in a little bit to double check to make sure that I'm not interpreting it wrong. Yeah. So it actually does kind of hit this piece in the center like that. A little bit more like that. Okay, let's put in a little bit of some units so that it makes sense what we're seeing. My window, let me go back to the -5 to 5 so I can see my marks on there better. It's going out to being less than 1, so this number is less than 1. And then it looks like it's extending over to 4. Is that what yours looks like? 2, 3, 4. Okay, so it's not a great scale. My scale is definitely off. And it looks like it's crossing at about 2 right here as well. Something of that nature. Just an FYI, on page 725, there are names given to the different kinds of shapes that are being drawn here. This one's actually called a cardioid. Yeah. So if you're interested in some of the names that do these, you're going to find some very interesting shapes showing up as we are in this particular section and in 10.5. Cardioid is this one. What's that? Yeah, it is vaguely heart-shaped. You're right. Yeah. All right, so let's move on to another one. Our directions are going to be similar, but they're going to change a little bit toward the end. We're going to sketch the graph. So that part's kind of the same. We don't really want it to be too short in terms of my theta, but this one doesn't specifically say it can't go too long either. But the other part of this directions are that they want us to find a corresponding rectangular equation. Now, this particular one, we could do it strictly from a graphical perspective because the one I'm going to give you is a really straightforward, simple equation. In general, they're not going to always be so nice looking, so I'm going to show you it also from an equation standpoint, how we change them around, and then we'll verify that the graph actually makes sense from there. So the equation that we're going to look at, this is number 5, is r equals 2 sine theta. So graph it on the calculator, 2 sine theta. Obviously it makes sense that my window would go from 0 to 2 pi. This is a very small window, so -5 to 5 should be just fine. What graph does it give you?
Circle.
It's a circle. It looks like an ellipse if you're in like a -5 to 5 window because the scale is off because it's a rectangular window you're looking at it. But it really is a circle. Again, if you do zoom square, which is zoom 5, it'll square it up and it will really look like a circle now. So this looks like a circle, and it's a circle that's like that, roughly speaking, sort of hitting the x-axis at the origin. Okay? Now, it's got a radius of 1. You can see where it's centered. You know how to create the equation for this. That's not really a big deal. I could do that in the later part of a college algebra class, and they could manage that. But it's not always going to be a circle, right? What if it had been the cardioid that we got on the last one? And then there's other equations, too, that can show up, and you wouldn't know what they would be doing. So let me show you how we think about this in terms of changing it on a graphical or on a equation standpoint instead of a graphical standpoint. So our R equation is R equals 2 sine of theta. We'll take a look back at the equations we had. They were back over here. In fact, I'll copy them and paste them so we have access to them over here in this bottom corner. So we're going to be using these equations to make our changes. Whoa, where'd that go? All right, there they are. And we'll do there. Hopefully, as you're looking at this, you're like, okay, well, I've got 2 sine theta, and that looks an awful lot like that one at the bottom that says y equals r sine theta. And it does, right? As long as the r were 2, that would actually work just fine. If it was a little less obvious, what you could actually do is you could solve that. So this is y equals r sine theta for sine. So if we solved this for sine, then the sine of theta would equal, another form of it anyway, y over r. So up in our equation, I can leave this as r. This is a 2, and the sine can be written as y over r. Okay, everybody good so far? Okay, So we're going to solve this now, or simplify this now, excuse me, clean it up. So I can multiply my r to the other side, so I have r squared now equals 2y. The goal is not to have r's and thetas. I've eliminated the theta, now I need to eliminate the r. Well, what is r squared? Yeah, down at the bottom, it's x squared plus y squared. Now, technically speaking, I've done what the directions asked at this point. This is a corresponding rectangular equation, but it's not in a very familiar to us form. Agreed? So we're going to manipulate it a little bit more to put it into a form that looks more familiar to us when we have the ability to do so, and we certainly do here. We know it's supposed to be a circle. We saw it on the calculator. So we're going to shift the 2y to the other side. So I have x squared plus y squared minus 2y, and I'm going to leave a space, and right now it equals 0. And if you'll remember, what we can do here is we can complete the square. So we take the middle term, that's the 2, negative 2, excuse me, we divide it by 2 and we square it. So what's negative 2 divided by 2 squared? So negative 2 divided by 2 would be 1, and then 1 squared would be 1. And we can ignore the negative, really, because we're squaring things. It's going to eliminate itself. And if I add 1 to the left, I have to add 1 to the right. And then because I used completing the square, the reason I did it was to be able to factor this into a perfect square trinomial. Looks like that. And it equals 1. So that's the perfect square factoring for it. And if you look back at the graph that I've got still on my screen, that's it, right? This is the center, 0, 1. It has a radius of 1. All of that makes perfect sense, right? Not the circumference, but the diameter is equal to 2, all that. So this is the equation that we were looking for right here. So that's friendly when we have something that's familiar to us. We're going to do another one that's a familiar to us type of equation, but we're going to convert in the other direction. So we're going to convert the rectangular equation to polar form and graph. And the equation we're going to use is y squared minus x squared equals 4. Now, it's not in standard form of this conic, but do you remember what conic this is?
Hyperbola.
It's a hyperbola. How did you know, Jubal?
Because it's minus in the middle.
Yep, and they're both squared too, right? Yeah, so there's a subtraction sign between them. Their signs differ. One's positive, one's negative, and they're both squared. So this is a hyperbola. And if I were to put it into standard form, I would just divide every piece by the 4 that's on the right-hand side. I would have y squared over 4 minus x squared over 4 equals 1. And we talked about how we would go about graphing that so that we'd have a perspective of what this should look like, right? So that's not what our goal is right now, but we could graph this. We did that back in section 1, 10.1. What we're wanting to do here, though, is we're wanting to change this equation with our x's and y's into r's and thetas. So I need to know what is y and what is x, and I need to do some replacements. So what does y equal? R sine theta. So this is r sine theta squared. What does x equal? Yeah, r cosine of theta, which we'll now have squared, and it equals 4. All right, so r sine theta would be r sine theta squared would be r squared sine squared theta minus r squared cosine squared of theta. And while it isn't able to sort of condense as a Pythagorean, right? It's addition. It's not, if it were addition, I could factor the r squared out and I could condense it down. I can do that, but I can't do it with the Pythagorean theorem. So we're going to factor out the r squared. If I'd had an ellipse, this would actually be able to be a plus right here, but it's not. It's a subtraction. and it looks like this. Okay, everybody good so far? So once again, you know, like the very first step where I substituted in then into the x and the y, the r sine theta and the r cosine theta, technically now I'm in polar form. It's just not cleaned up very nicely, correct? And so there's actually a nice way that we can condense this, and I won't make you go back and learn or memorize these, but they are posted inside of Canvas. These are trigonometric identities, okay? You're welcome to use them when we get to the test. I don't have any problem with that. There is a nice way, instead of writing sine squared minus cosine squared, right? And that's actually a double angle. It's, which one is it? It's the double angle identity. Yeah. So the double angle identity on this sheet, just to let you know, it actually says cosine of 2a equals cosine squared of a minus sine squared of a. Now, that's not exactly what we have. We have sine squared minus cosine squared, not cosine squared minus sine squared. So how will that change our value? Yeah, it'll just be negative cosine of 2a. So we're going to use the r squared here. This will be negative cosine of 2 theta, because our angle is theta, equals 4. Our goal is to have it solved for r, right? Because your calculator won't let you put it in an r squared form, just like when we're doing with functions and we have, y squared equals something. We need to find a, solution for r. So we're going to do r squared equals, so this will be negative 4 over cosine of 2 theta. And then I will need to square root, and I have the positive or negative square root of, and it feels odd for us to write this, so bear with me. I know it says negative 4 underneath a radical. But that's not always positive, and that's not always negative, right? Yeah, it's wherever cosine is negative that this will work. Agreed? So think about your unit circle. Where on your unit circle is cosine negative? Okay. Huh? Yeah. So cosine is negative here and here, right? In quadrants 2 and 3. Cosine is the same as your x value, if you think about it that way. So between pi halves and 3 pi halves. It's going to be valuable for us to know that, because otherwise the calculator is going to have problems graphing this, right? If I don't choose a window for my theta that makes sense, the calculator won't be able to make sense of it either. Okay, so my theta value here needs to make sure that it goes between and strictly between pi halves and 3 pi halves. Do I need it strictly between? Let's think. Yes, because I don't need my cosine value to equal 0. That would give me an undefined value as well, so strictly between. Okay, so grab your calculator. Of course, just like when we have functions, we can't enter a plus or minus very friendly into there. And so I'm just going to enter R1 is equal to the positive 1 and R2 is equal to the negative 1. So in R1, I'm going to enter the square root of negative 4 divided by cosine of 2 theta. Make sure you do have 2 theta. And then I want the opposite of that, so I can actually enter a negative and type it all out again, or I can enter negative. So my Y1 looks like this. I don't have the nice text versions that some of you guys do, so that types it out looking pretty, but this is what mine looks like, actually. And they aren't Y's, they're R's. R1. In R2, I can actually put in negative R1, and the way you get R1 here is by hitting vars, the vars button, going to its Y vars, and then I go to polar, and I go to R1. So you get vars, Y vars, polar, R1. It will take the equation you had from R1 and put it into R2. And you need to make sure before you go hit and graph that your window does what you just said it was supposed to do. Your window needs to go from pi halves to 3 pi halves. And we don't have a real good idea of what my window needs to be. I'm going to go negative 10 to 10 since I'm not sure. This is a hyperbola, so it's not going to be nice and compact. It's going to continue on indefinitely. does kind of look like a Nike swoosh. Oh, yeah. You might know graph in colors, unfortunately. All right, so it looks like it stops short of kind of finishing it out on mine. Does yours look like that too? Yeah, and I don't know why it does that. I feel like there's an error in the way it's calculating something because it's all there. We've done the problem correctly. The calculator has a miscommunication issue in doing so. Oh, no. I know what's wrong. We didn't do one more step. I take it back. I forgot about that. This is the theta values that we need, but we need it to be for 2 theta. Our angle is 2 theta, not just theta. That's what's wrong. So we need to actually divide by 2. So we shouldn't actually have it go from pi halves to 3 pi halves. It should be going from pi fourths to 3 pi fourths. Let's try that. Oh, I don't even know if I have mine. No, I do have mine right. Pi over 4 to 3 pi over 4. All right, worked earlier. Let's see if I can get it to work this time. Oh, that's better. Did it work now?
I graphed the same, like the curve together like earlier. It was like graph and then part.
Yeah. Okay, did it work? Yes? Wonderful. I'm sorry, I forgot about our double angle that we changed. Okay, I have one more example. Are you ready? Sure. One more in 10-4 anyway. All right, we're going to convert the polar equation to rectangular form. And graph. And this will be a familiar graph to us, at least when we change it into our rectangular form. So this is r equals 4 cosine of theta. We've seen one similar to this today. If you wanted to in your calculator, you could graph it so you could have some idea of what you're expecting to find. It's 4 cosine theta. The angle is just theta. It's not 2 theta or something like the last one was, so making it go from 0 to 2 pi seems quite reasonable. And you can let your window be whatever makes sense for it to be. Did I get that in there right? 4 cosine theta. Okay, so it looks a little funky because I've chosen to use a negative 10 to 10 window on mine, but what's the graph supposed to be? Looks like it should be a circle. Does it look like a circle on yours? I mean, visually it looks like an ellipse at the moment, but you can pretend that it should be a circle if we squared up our window. All right. So we're going to do the same thing that we did on, I can't remember which problem it was, this one. We're going to use our equations to change our r and our theta into x's and to y's. So we have done this for sine a moment ago, so we'll do it for cosine now. So x is r cosine of theta, which means that cosine of theta is equal to x over r. So up in our equation, I now have r equals 4, and then I have x over r. So this is r squared equals 4x. And we've seen r squared and done this before. It's x squared plus y squared equals 4x. And then we will shift this to the other side. So I have x squared plus 4x. I'll leave a space. Plus y squared. What was that?
Minus 4x.
Yes, thank you. It's right on my paper, just wrong on the screen. All right, so what do I need to add to complete the square? 4. To both sides, right? Yep. And this will factor as x minus 2 squared plus y squared equals 4. It's a circle, right? Centered where? Centered at 2, 0. Okay, that looks like this. And it has a radius of what? 2. So I didn't put my grid on, and I'm not going to at the moment, but if I go 2 in all 4 directions to get my perspective, I would be somewhere like this, and then I would connect my dots, and it approximately would go like that. I do have a very fancy circle tool on here to be able to draw. I always have to move them, though. Every time I draw them wrong, so just get used to it. Yep. All right, any questions on that? All right, so the equation itself, I kind of have things running together that we were looking for. Whoa, that wasn't it at all. How about that one? We'll use that tool. That's our equation. That's our answer to the question. And then we have our picture that we were sketching as the other part of the answer. All right, so homework for this section. This is page 726, problems 9, 12, 17, 22, 29, 32, 39, 42, 45, 48, 82, 87, and 90.